Alrighty, folks, I hope everybody's doing well, and we're going to jump into module number 6, which is about performance. Okay, so we're going to shake things up a little bit today in this lecture, and you're going to have a little bit of time to do an activity that'll be sort of on your own and part of your in-class activity. So before we get started, though, I want to talk a little bit about who this gentleman is. And maybe you've seen him come up in the assignments, but does anybody know who this is? You can go ahead and do a quick wiki search if you want, but this is a famous computer scientist. You can see he even has a name tag on here, but this is Donald Knuth. And he is famous for saying, he sort of had this saying, premature optimization is the root of all evil, or at least most of it in programming. Okay, so the key here, and there's a little bit of context to this quote, it's a very famous quote, but it's often misquoted, is this idea of premature optimization. Okay, so that is taking a look at your code and trying to make it the most optimal piece of code possible. And I'll give a little bit of wisdom to this because it really is not necessary, and it's not necessary yet in this course, to really optimize your code, right? We're trying to learn some of the basic ideas about how ray tracers work, get some intuition, and as we go sort of iteratively refine our code. You're even going to see in the Shirley text, which we've been following, that the code is pretty simple in a sense. You know, there aren't fancy tricks used unnecessarily, but and there is room for optimization, which we'll certainly talk about. But what we also want to talk about, though, is that never optimizing when there is an opportunity is also sort of evil. Okay, so we will want to figure out some data structures and so on to speed up our programs and perhaps look at opportunities for where we can speed up our code. Because again, iteration time is going to be important for us in this course as we move forward. It will be useful, and we will implement some data structures to do that, for instance. Okay, so that's the idea, and you can actually look up this quote and try to find the full context to it, because again, it's very misquoted, in which people think this means never optimize. So that's just what I want to get across here, some of my wisdom coming to you guys in this course here. Okay, so anyway, last lecture before we get into today, we talked about how cameras work, got some intuition about how they work, the sort of general idea, what we're replicating with our virtual cameras, and we took some time to talk about a specific function called the lookat function. And I hope folks also had time to look at the Pixar in a Box lessons, because those are also quite good and fun to see and interact with a little bit on the lookat function. And again, what exactly is going on with some of these things, such as the other effects for anti-aliasing, and again, one that's covered in depth in the Pixar in a Box lesson, the depth of field. So we talked a little bit about that, anti-aliasing, and basically these jaggies that appear on our shapes, and why they appear, because it's really just a sampling issue, right? If we had more pixels on our monitor, we essentially have infinite in our real world. That's why things look pretty crisp, right? You don't see jaggy lines and so on. So that was one issue of our sort of image quality, and one thing that we want to fix up, and then the depth of field. So this little trick that we can focus in on an object, whatever the sort of key object is of the scene, I would say. So again, you know, if you look at this scene here with the caterpillar, you can very clearly see that's what we want to focus on, so we make everything else a little bit blurry. Okay, and there was a trick for doing that with this sort of circle of confusion, as it's called. And Shirley just alerts to this as the sort of disk, where he's going to sort of offset randomly some of the rays that are cast so that you sample and sort of blend in pixels here, and then you get sort of these blurry things that aren't the focal point in your scene. Okay, so for today, logistics, keep working on A2. That deadline's coming up, and I'm going to also be sending out an A3 later this weekend. Again, A3 is going to be perhaps a little bit of a lighter assignment. Again, if you're just going through the book and implementing everything, you're going to be in good shape, but you'll see what the requirements are. And that's also, I'll put myself on the screen here for a second. That's a little bit of a different part of this course. I hope you are enjoying it, but since you have a little bit of freedom, and I want everybody to build this thing, your ray tracer from the ground up. So it's a little bit different than my other graphics course if you've taken it, in that you're building all the code and don't have the support code with you this time. So anyway, so A3 is going to be released. I made a mention of what that is. It's going to be focusing on the camera and sort of capturing your scene from different viewpoints. So that's what the requirements are going to be for that. And of course, if you have any questions, feel free to drop by office hours. Since we have a small class, those are set up by email, so just email me at any time and we'll see you there. And I should also be giving you feedback on your assignment ones very, very soon. All right, so let's dive into and continue this lecture here. So today's key takeaways are going to be to understand just rasterization versus ray tracing. And this sort of makes sense to understand because we're going to talk about performance today. So we want to talk a little bit about this idea of what rasterization is. We've just kind of dove into ray tracing, so I want to sort of settle that. And then I want to get you to your task today, which is using a profiler. So this is something that has not been talked about. Maybe you've done it, maybe not, but just a little example for you, okay? So let's go ahead and start off with rasterization versus ray tracing. And you can see this little scene here. Let's see it a little bit bigger here. And if you take a moment to observe, these previous images here on the top left and the bottom left here, one is rasterized and one is ray traced. And I'll go ahead, cover up the left side, if you will, and go ahead and just see, can you tell any differences here? I'll give you a moment to pause and think about that. You can hit spacebar in the video to pause. If you're giving yourself a chance to pause and think about it, well, you can start to look at the spoon, for example, and see the reflections versus this one, which is quite dull, or even the cup here, which is reflecting a little bit of light here in the ray traced image versus rasterized one, or the teapot where there's reflections, right? So some of these things are much more difficult to simulate in what we call a rasterized image, okay? So the bottom left image, I would argue, is much more vibrant. The materials actually have different properties of how they reflect light or refract light. And it's just a little bit nicer. So you can sort of see the difference here. They've kind of computed some difference, highlighting what's different in the scene, things that are colored more, I guess. You can even see the shadows here, right? So I think the lighter pixels are just showing you what's different in the rasterized image versus here, okay? So the rasterized image, there's a lot more stuff lit up here, right? You can see the reflections. That's what's different between these. It's like a diff between these images, just if you're trying to interpret this. What's different between the ray trace and the rasterized? Oh, the ray traced has all this stuff, this reflection and so on, okay? So anyway, so you see something kind of neat there, and that's sort of motivating because we're learning about this technique in this class. But again, there's sort of two common models of rendering. In fact, there's many. But we've largely just dove into ray tracing. And again, it's not the only technique, right? Some of you folks, about half of you I had in computer graphics, where we dove into OpenGL. And that's a rasterization or an API for rasterization, okay? And that's the other common technique. And I just want to understand a little bit what's different between the two, okay? So how does rasterization work? And in part, it's going to be important to understand some of these terms because we're going to need to understand some geometry soon. But the idea is you start with an object like this triangle here that you geometrically define, right? You have some vertices here. These are each of the corners here. And then you establish some relationship between those vertices. So what the edges are by connecting them. Okay, so you have the edges, and then all these edges make up a polygon or a triangle or a face to draw that sort of geometry here, okay? So you need some sort of data structure for that. We are going to get into rendering stuff that isn't just a sphere as well in this course, but focusing on triangles so we can render almost any shape or approximate any shape. So anyway, that's sort of the structure. So we'll talk about what that structure is. But this is what rasterization relies on, right? Just drawing triangles, okay? So then our next stage, though, is we have this shape here. We know where the points are for each of the vertices and the edges. And now we want to fill in the pixels based off of where this object lies that we have plotted some place in a Cartesian coordinate system, and so on, and then fill in the pixels to approximate this shape, right? So if you've got most of this shape here filling in a pixel, then you fill it in here, okay? Then you repeat this process for other objects. You know, here's a triangle, maybe you draw an X and then another blue triangle on top of it, and you get this sort of final scene here, okay? You just repeat this process, right? Laying out your points, connecting the edges, and then filling in each of your triangles, okay? So again, you do this sort of iterative process for each of these triangles, and then just per shape that you have, so we're just working with triangles here, you sort of look through it and you decide, hey, do I want to fill in this pixel or not to approximate it? And if most of, you know, this shape here fills up the pixel, then maybe you fill it in. So that's what these green ones are. The red are saying, well, there's a little bit of a tiny edge here, so I should look and maybe compute, you know, what the area is, or, you know, you can use different techniques to determine, hey, should I actually fill in this pixel to approximate this shape? But that's what you're doing. It's sort of the scan line approach. Usually just sort of look one pixel after the other. There's other techniques, again, for folks who did graphics, you saw some of these other techniques, but this is the idea here, okay? So that's what rasterizing is. You're looking at, per object that you draw, which pixels you should fill in, okay? And you've got other things to take care of. You know, how do you order these different shapes? And perhaps I have different shapes and they, you know, partially overlap each other, or these kind of things. And there's something actually called a Z buffer to help you determine which pixel that you should actually draw, right? And we can actually do this. You sort of see this in the Shirley text. He's got this sort of like hittable object thing, and then you compute the distance, and then you sort of save you know, the closest pixel that you intersect with. Well, we sort of do the same thing with when we're rasterizing. So these shapes here, like this red triangle, for instance, is in front of the blue sphere. So we record for that shape what the nearest pixel is, and that's how we determine the color of that pixel per shape or per, you know, polygon that is overlapping. Okay, per polygon or per triangle. Okay, so we have a data structure for that, okay? So you can kind of see the different passes where we just have a blank canvas and we draw our rectangle here, the green one first, and we say, okay, here's the distance from all these pixels, and then we draw our red, or excuse me, the blue, and we say, oh, okay, here's our blue here, it's a little bit further away, right? It's sort of pushing in the backwards direction is further away. And then we draw the red and we say, okay, that's overlapping, you know, these other ones, so whatever the greatest value is what we keep. That's closest to the screen here. Okay, and then this draws our final scene, which is a little bit of green here, red, and blue. Okay, so just reviewing on this, I believe I showed this on maybe the second or the third lecture and just kind of hopped over it without talking too much about what rasterization is and comparing it to ray tracing. But, you know, we just want to understand for rasterization, we're looping through every object in our scene. So if I've got this Rubik's Cube, I'm just looking at all the Rubik's Cube polygons in just this region here, which I'm circling around with my cursor towards the middle of the screen, okay? And that's the sort of, that's what we're doing. We're just looking at what those pixels are in that object that's closest to us, okay? And then we draw that part of the object. Now, ray tracing, on the other hand, we're saying for each pixel, send out a ray and see which object it intersects with, okay? And as we learned with things like anti-aliasing, or if we're doing multiple samples, we can send out hundreds of rays per pixel and sort of offset them a little bit. And then we can actually, depending on where you are in the text, if you're simulating a reflective material, you can actually hit a material and then you can bounce again, and you can bounce again and bounce again. So per pixel, you're sending out a lot of rays and trying to test for intersection with a lot of objects, okay? So that's the fundamental difference here, where rasterization, you're just sort of saying, hey, I have this many pixels, I just want to see which object is closer. And you're sort of just testing that, okay? And once you've looped through every pixel on your screen, you're done. Ray tracing, not quite as simple, right? You're doing a lot more work, okay? Which is better, depends what you mean by better. I'll ask that in another way momentarily, but you'll see that these two scenes are pretty similar, right? You've got some different materials. It's, you know, if I put these side by side, they're a little bit hard to differentiate. But of course, with your eyes in this course, you can revisit this image and you will notice things that are different. But, you know, historically, again, the trade-offs have been ray tracers better simulate materials because we're thinking about light and physical properties, right? We've probably maybe it's been a surprise the amount of physics and light and some of these things that have popped up in this course, but that's really how we want to think of things and sort of have that mindset. So we can get more realistic images that are generated because we're trying to simulate how things look in the real world by their physical properties and actual physics. But the trade-off is that this can be a lot slower, right? It could have taken hours to generate a single image, or even days sometimes, okay? There's ways to speed it up so it doesn't take, forever, but this technique does take longer because, as mentioned, you're doing for each pixel, you're testing which object's closer and potentially doing multiple tests per pixel. Okay, you could have hundreds of rays per pixel. Each of those rays can sort of bounce around as well, so that makes things a little bit more complex. Rasterizers, on the other hand, usually end up with a less realistic image. There's tricks to make things go fast. Even for the reflections, there's different tricks that you can use. And because it's faster, you can take advantage of this and use it in real-time simulations or interactive applications, okay? So again, which is faster and why? Go ahead and pause the video and see if you can recall to yourself the answer. And if you've taken a moment to pause the video and think about this a little bit, just to kind of refresh and, again, just understand this main concept of what you're looping through. You're looping through objects, or you're looping through every pixel, right? How many pixels do you have on your screen? Mine's at least 4,000 by 2,000 pixels, roughly, okay? So that's a lot of pixels to loop through every single scene, okay? And we'll have some ways to speed that up, but we got to understand what the problem is first, okay? Versus rasterization is, for a few objects that you have. Even if you have objects that fill up the entire screen, we're going to find that we have hardware that can still, filling in the pixels is actually the easy part once you mitigate that task to the hardware, okay? So again, it's going to depend on, maybe if you have more pixels, how fancy you're getting, right? We can do a ray traced image in real time. It just won't be very fancy, or it won't look very good, okay? And it probably still won't be as fast. And there's ways to do it in a hardware. But again, this rasterization technique is typically going to be faster. And then we'll talk about combining these two in a hybrid approach, probably towards the very end of the class. We'll get into sort of hybrid stuff, okay? So anyway, rasterization is sort of the faster or the right tool to use for interactive and real-time applications. Okay, so that's the idea. That's what this is sort of discussing here. But we sort of start running into problems, and this wall of text here is just describing that. When we start looking at some of these reflections here, or this glass here, I mean, even look at this glass here compared to this one here. Which one's more translucent? Is there a shadow here? So there's sort of an interesting shadow here with the glass where you can see the shadow and sort of some light beams that might cross through it, and you get sort of this caustic effect here. Versus this one, it's missing, right? So when you look at these two images side by side, I say they're the same, but you start to notice this is where rasterization starts to break down. Like, how do you simulate that with just polygons, that there's this sort of caustic material here that's, if you fill up a glass of water next to you and shine a flashlight through it and look at the shadow, it looks a lot more interesting. It's not just this dull sort of black shadow here, okay? So that's where rasterization starts to break down once you're starting to simulate materials, get reflections, even transparency, some of these things, and when you have lots of lights in your scene to capture all those effects. Okay, so that's where we need these offline rendering or non-interactive techniques like ray tracing, which we're talking about, to spruce up or make our images much more beautiful. Okay, and of course, though, that comes at a cost of time. It can take a day to render an image, a single image. Of course, you can parallelize that, which we will talk about. So it doesn't always take a day. That's what they do at Pixar and so on. But that's the idea. Okay, so that's the limitation of some of the limitations of rasterization. Just wanted to kind of get you in the loop of that. We've been diving into ray tracing stuff, but just so you understand what the trade-off is, because the real dream is that we have real-time ray tracing so that we can see, and simulate all these awesome effects in real time, okay? So the trend is that we are going to have some real-time ray tracing, because this task, as I alluded to, is what we would say embarrassingly parallel, meaning, we could have a piece of hardware that has lots of threads, and we'll review threads if you haven't taken systems or haven't taken it in a while, where basically each pixel is a thread, okay? And we can accumulate over time the color of our different pixels by having multiple threads performing this ray tracing task. And this is what we are starting to see today. And by today, I mean around or 2018, I would say, is when this hardware came out, if my memory serves correct. So very, very recent. We're on the sort of cutting edge of ray tracing and learning these techniques. That's, again, why I think this is a super cool thing to see here. So this is what's called the Turing architecture here, and you're going to see it has different cores. It's really a marketing term, but there are supposedly, these sort of dedicated ray tracing cores. I don't know if your chip's technically divided up like this. Have to talk to our hardware person. It's more of a marketing thing, but there are dedicated ways to access the hardware for ray tracing tasks. Let me say that here, okay? So that you can have your actual hardware, and your hardware is dedicated to doing a very specific task very well to this ray tracing task here, okay? And because we're getting more memory and more resources, more speed on our graphics cards, this is a good thing. So eventually we'll be able to push this ray tracing task onto hardware and do things in real time, and simulate some really, really cool effects, okay? And reduce the time to generate our images. And as I mentioned, maybe we'll get to that. I'll need to think about that because the problem is not all of us have RTX enabled cards, which is what NVIDIA has produced here, this Turing architecture. But we'll think about that, or at least we will discuss it again at least once more in this course. Okay, so again, from a hardware perspective, how this is going to differ, again, because these are two different techniques, and again, why rasterization is sort of the common one is because that's what the hardware supports, okay? So if the hardware supports it, we can do it fast. We have a sort of pipeline of how we can perform these tasks, and for my previous computer graphics students, this will look familiar. For those who haven't taken computer graphics, just know that you're usually doing one task after another, just like our ray tracers that we're setting up. We are first creating some objects, then we're casting some rays, we're computing some normals, and then we're testing, what we intersected with and what to highlight, right? That's a process. It's the algorithm that's followed. You can call it a pipeline. But so with ray tracing, we're going to have that same pipeline in real-time ray tracing again. So this ability to send out some rays, sort of schedule, hey, I want to shoot out, 100 million rays of light in my scene, and then wait a little bit and have a dedicated part of your hardware handle that task, and then retrieve the result and maybe test some things like what object did I intersect with. Okay, that's the stuff that's going to be handled in the hardware eventually. Okay. So again, that's these RTX cards. Maybe you have one, maybe you've seen one. They're starting to become more common, even in laptops. I've got a laptop with one, luckily enough, that will be able to support this pipeline here to do the real-time ray tracing. Because again, what are the needs? Well, per pixel, we need to be able to fire out a ray and test if it intersects with an object, and we want dedicated hardware to do that. Okay. Okay, so that's a lot of stuff in a little time. And so if you need to go ahead and take a little break, please feel free. And then we'll move to our next topic. Okay, and if you're giving yourself a little bit of a break, and we will resume to talk just a little bit about performance. What can we do today about this problem? And this is actually something you're going to take over in your in-class activity. We would have a little bit of fun with, but I want you to sort of have your ray tracers, whatever shape they're in. So maybe this will be a Sunday night activity, but they'll talk about it and I'll show you at least one tool. But to be able to measure the performance of your actual tool. Okay, so how do we measure performance? Well, there's a simple way to do it. If you're doing it on the command line, for instance, and you can open up a terminal, and we have this program time that you can run. So you can run time, and then whatever program you're running. Let's see if I have one here. I don't know what it is. Okay, but it'll run this program and report to you the time spent for this program to run. Okay, so that's one simple way we can do it. So I ran this example. I had a linked list, which searches through 100,000 items and sort of changes their values. And these are the sort of times that it took to do that task. So we're getting some information. We have some baseline of our performance in our code. Okay, so real time is the wall clock time. So again, if you had a clock on the wall and we're just looking at it and counting the seconds, this is what real time is. User time is how much time your CPU actually spent running the process. So it should never, well, let me be careful with this. So usually if only one core is running, it'll reflect, something similar to this real time here, okay? And then the system time, which is down below here, is how much time your operating system did something else. Maybe it context switched and then another program was running in the background. So that's the time the operating system spent doing some stuff in the background, okay? So it was not actually just executing only your program. Operating systems do a good job of giving us the illusion that that's what happens, but that's not actually what happens. So you'll have a little bit of time here. So that's what those metrics are. Now, if you have multiple cores, I just want to allude to this a little bit, and you have multiple threads running, it is possible that the user time could be twice the real time, right? If you have 2 cores doing the same task, and that task takes them each 2 minutes, then your user time might show up here as 4 minutes and 18 seconds. So be wary that the user time could be greater than the actual real world time, okay? And that's how a studio like Pixar is able to generate a frame in a movie that would normally take a day by parallelizing it, so it'll show up in the user time. Maybe it took a day of CPU time, but the real time might be a few minutes for that frame. Okay, so just a sort of start there. So that's the first thing that you can start doing to start measuring time here, okay? But what I'm going to ask you to do is to find a tool that's a little bit more specific here, okay? And the tool that I'll discuss is called Perf. I'm on Linux. There's a bunch of tools. If you want to just look for example, profilers on Windows or profilers on Mac, you can do this sort of Google search. There's one called OProfiler. And it depends what tool you're using. Even if you're using JavaScript, so let me go into the developer tools. And it looks like, oh, Google's failing on something, but you can see there is a performance tab. So if you're doing your ray tracer in JavaScript, you can click the record time. It'll collect a profile here. You can click stop, and you can figure out how to sort of run this within Node.js and these sort of things. And it'll give you a little report of how much time did I spend in different functions. This function called this function called this function, and it took some duration of time here, from 500 milliseconds to 800 milliseconds. And each of these that I'm clicking on here, whatever this function is here, I don't know what the browser is doing, but it took, a few 372.44 milliseconds, so about 0.4 seconds to run these tasks on this page here, okay? Or maybe to do this query or load it up or whatever background task. So that is the idea. So Perf is the same sort of tool for Linux here, where you can measure performance. And these tools, you can use them on command line. They can be part of your IDE. They can be a web tool, like a browser. It just depends what language you're using. Even Python, if you're doing a ray tracer in Python, will have that profiling, those profiling tools available. You just might have to download one. Okay, so that's what I'm going to want you to do. And the idea here, and I'm mostly just interested in time, so perhaps the CPU clock time, for example, and we just discussed what that is. That's the user time here, back from this metric. But the idea is you can run perf, grab some stats, and then the events that you want to count, or whatever they are, and you can have multiple, but this is CPU clock time, and then your program. So I had a little linked list, so I can do /list here. And you can see how much time elapsed here. So when I ran it with perf here, apparently it just took 1.8 seconds on this iteration that I ran it in. So there will be some variance here, but that's the idea. So you can start to gather how much time does it take in your program. But we want to go a step further here, okay? So what profilers are really good at is telling you where you spend your program time in. So for us, it is going to be useful because we're generating an image. We'll want to know how much time it takes that image. So, even as things get more complex, you can know if you have time to go get a coffee towards the end of the semester when you're generating your image. But otherwise, where would you be able to speed up the program if you needed to? So perf, if you're running from the command line, has this thing called record or record, and it'll get the record of how much time you're spending in each of the functions. So here in my linked list here, it looks like I have a, and this is in fact what I have, a function.length here, and I'm spending 74% of my time here. And I have another function here called .set node value, where I'm spending 12% of my time, and get node value, 12%. This program's just sort of walking through a linked list and setting node values to different things, okay? But it's computing the length a lot. So somewhere in my code is being very inefficient, okay? So it doesn't really matter what this code's doing, it just matters what the report is showing you. And what I'm gonna want you to do in your in-class activity is just to report on where your code is spending the most time. Is it in the intersect function? Is it in some math function? Where are you spending a lot of time? And then we'll think about how to speed that up, what kind of data structures we can have, and so on, okay? So anyway, in this perf tool, it's sort of giving a visual indicator of this code. It's in red to indicate hot, meaning you're spending a lot of time there, so it's hot code. So to sort of loop things together with the Knuth quote that we started with, right? Premature optimization is the root of all evil. But now that we know we're spending lots of time in our code in this length function, maybe in this data structure, I could just include a member variable for length, and then I will not spend a lot of time here, right? And I'll trade a little bit of memory for that ability to not recompute length every time from scratch in this linked list, okay? Let me actually bring up the code example. I believe I have it on another slide here. Let me see if I have it with me. Or I can dig it up here in just a moment. And here's a little slide where I captured this from, but this is the idea of what the linked list is doing. So let me just go ahead and highlight this here, where I'm computing the length and passing in whatever the linked list is every time that I execute this for loop. So this would be sort of a silly design in my C program and something that would be a huge bottleneck in my ray tracer here, okay? And then you can see what the actual code is here, where I'm just setting a node value here and then getting the node value, just something kind of trivial here, right? So the speed of this code, I'll actually just watch you through, is at least, O of n here. Because I have to compute the length of the linked list every time. And this function is not just returning the length, but it's actually walking through the entirety of the linked list. Right, so some of these things are harmless when we're first just trying to get something up and running, and that's the right thing to do in this course for now, just get things working. But eventually we will want to think about performance as our images take longer and longer to generate. So you get the idea that we could just store in a variable what the length is, just compute this one time, just store it here int length equals, compute this one time, or even just store as part of this data structure the length of the linked list, okay? So anyway, then you would know where to optimize your code. And that's exactly what the profiler tells you, where you're spending your time, so that when you run your program, you can optimize there. And we have a unique opportunity to sort of use our profilers here because our images that we're generating are generally pretty deterministic, right? There's a little bit of randomness in how we maybe move some arrays around or do some sampling and some of these things, but they're relatively deterministic images. So we know it is going to take this perhaps path here, whatever the hot path is in our code, of casting rays and testing intersections and all these sort of things here. So that is to our advantage that we can do that. And in our actual code, okay, and use these profiling tools, okay? So your task, this is actually going to be your in-class activity, is going to be to search for a profiler for your language that you're using, make sure it runs on your operating system, download the program and try it out and see if you can find or identify the bottleneck in your actual program. So I'll just be asking you, what operating system are you using? This also will be some good data for me, so I'm able to test your tools out and so on. But for you as well to get a little bit of experience with performance. Okay. So some other quick performance tricks. I want to leave you time to do that as sort of a in-class activity, outside of class, of course. Here we're all virtual. But some other performance tricks that you might try. And these are just a low-hanging fruit here too to speed up your iteration time, because this will be something I want you to think about a little bit. But for folks, and this is a little bit skewed towards folks using compiled languages here, So if you're using C or C++ or D or, Rust or, any language, find out what you're using. You might have optimization flags. So when you're just compiling your program, you can just pass in a flag O3, and the compiler will try to do smart things and transform your code for you and generate optimal code. Okay, that's not something I super want to get into in this course. You're welcome to explore my other courses for that. So if you're wondering about where did that optimization slide deck come from, that came from lecture 9 here on my Fall 19 systems course. And then I have the whole class dedicated to performance engineering here, which might become an official class as well. But so you can read about these ideas. But this is just a low-hanging fruit here where you can speed up your program. I'm comparing here C with Python, but just 2 C programs, you can speed it up about 6 times by just passing in this compiler flag. It'll probably take a fraction of a second. Maybe it'll take a little bit longer to compile, but only a little bit longer. And you get a program that's generating images 6 times faster. So it's a low-hanging fruit for you if you want to try to speed up your programs. I don't see a lot of people talking about these kinds of things in the curriculum, so if you haven't seen these tricks before, you can do this, right? This is how you do it in C. In Java and so on, there are other optimizations you can use to improve your code generation. I believe even in JavaScript, there's tricks or different tools that you can use, right? You can compile your JavaScript to C and all these sort of different tricks as well. So just something to keep in mind to utilize your tools and your compilers. I'd rather bring that up now earlier than later, just so you can, if it's taking you a long time to generate some of these images, depending on what hardware you have, you can speed up your iteration time, okay? But it's not something to be bogged down in some of these other tricks. Focus on the profiler for today and just building the ray tracer. Okay, so that's what I've got for you. I want you to spend a little bit of time. I think it'll take you a little bit of time just to research some different profilers, find tools that are for free. If you have any troubles with that, let me know. Please reach out on Piazza or so forth. And maybe what I'll do is compile the results for this in-class activity. I'll sort of be doing that myself, but I'll try to share those on Piazza as well. Okay. So that's it, folks, for this week. A little bit of a shorter one here, but I wanted you to play around with your and be able to finish your ray tracers so that you can actually do this profiling experiment and just see where you're spending time in your ray tracers. All right, we'll talk to you soon. See you in the next module.